So to get going with this simulation, let's first take a look at the mesh. I set up the mesh using an edge distribution. This allows me to specify the number of elements, and in this case I used an arithmetic sequence with this element ratio of 4 that will give me closely spaced points near the ground surface on this end and more widely spaced points over here at this end. If I zoom in on this end a little bit, you can see the points, and if we zoom out you can see that they're more closely spaced here than as we go deeper. So that's because the gradients will be steep right here near the ground surface and much less steep as we go deeper, so we put more points near the ground surface. If we find that there's some oscillations numerically, we could add in some more points there. Okay, so the analysis is done with 3 study steps. Well, a total of 4 steps here. The first 3 show how to analyze each one of the steps in the test individually. The first one does gravity equilibration. Then we add water to the top and raise the head, and then we allow that water to redistribute. So if we look at this study and expand it out, we see that the analysis is set up with times that are shown here. This is a fairly broad range of times. This goes out 10 to the 7th seconds, and I did that just so that I would give enough time for this analysis really to fully equilibrate. I always like to have results while solving to keep an eye on the analysis, and this is pretty important here. The physics and variables section, what I've done is to set this analysis up, I selected the boundary conditions that will be valid for the gravity equilibration step of this analysis. So as you recall from the earlier video, there are 3 types of boundary conditions that we're going to use in this analysis. And for gravity equilibration, I want to specify that the flux at the ground surface is equal to 0. That's done with that boundary condition, and these other 2 boundary conditions are disabled. So that allows me to tailor this particular study to use the kind of conditions that I need to do this analysis. And if I go on to the next study, this is where water is added to the top, and I expand that out, and I see a similar thing. The physics and variables section pops up, and I've checked this box here so I can modify the physics tree. In many analysis, you don't really need to do this, but for this particular one, because we have these different steps where the boundary conditions change, we do need to use it, and it's really quite a powerful feature. So in step 2, we've switched boundary conditions from the mass flux shown here to this one. This pressure 3 boundary condition is the one that's active. And if we want to find out what this pressure 3 boundary condition actually does, then we can go back up here to where the physics are specified and the different boundary conditions are described there. So we could select that and go take a look and see in detail what's going on. But we did that in the previous video, so we'll just move on here. The other thing that's going to be important about this study is that we use the results from the previous study for the initial conditions, and that's shown here with its values of dependent variables. And so we want to set that up like this. It's user control. The method is solution, and the study is study 1, gravity equilibration, which is that study, the previous study, and we select the last time. So the final solution from the previous study is used as the initial conditions for this one. So that's the setup, and let me see. I also have some results while solving, and go on to the third study, and it's going to be quite similar we specify the physics here by changing the boundary condition to that boundary condition, and we have the initial conditions set up to use the last value of the previous study. Okay, so these three studies will allow me to do the three steps in the analysis in sequence. And I do one, I get the results, and then I run the next study. So that works great. It's a good way to set the analysis up initially to make sure everything is working okay. But what we're going to want to do is ultimately combine all of these studies in one. And that's what's shown here in study 4. And the way I'm doing it is by having these three study steps included in this one study. Okay, so the way to do that is go and right click and then go here to study step and add a time dependent study step, and then set this study step up. This will give you a screen that looks like this, that looks pretty much the same as the screen that looked like that. See how that says step 1 time dependent? Down here there's step 1, and I have these multiple steps in the same study. What I had previously up here is each one of these studies only had one step. But now I've got multiple steps, and this really expands the capabilities that I can draw on for my analysis. So what I'm doing is in this step 1, I do the calculations that I would have done right there. I allow the solution to run to equilibration, and then in this study here I add water to the top, and you can see I've selected the right boundary condition, and I'm using the initial condition from the previous study. So all things that I learned about up here, I'm now implementing them all in one study down here. Okay, so I do that, and if I didn't have this node selected, or if I disabled it, then I could run this, and this will run the analysis, all three steps in sequence, and give me the result. So let's see. You can see there it is. There's the data, and then the blue line is the calculation. This is now showing the water content at my observation point. Okay, so that's how this analysis is set up, this study 4. It'll run all three of these studies at once. And this is what I'm going to need to do when I run the optimization, because when I change the parameters in the soil moisture retention function, I'm going to need to let it re-equilibrate and then add water and then let that water redistribute. Okay, so this all is going to be necessary for optimization, and let me show you how to set up the optimization for this. If I right click, I can add that optimization node right there, and if I expand this out, let's just take a quick look through this optimization node. There are several methods of optimization you can pick. This Nedler or Nelder-Mead is the default, and it comes with a default optimality tolerance of 0.001, and I've made it a bit tighter for this analysis, but I would recommend that you experiment with that. And okay, these are defaults. Now you're going to have to specify an objective function in order to do this analysis. The objective function will compare some data to calculated values, and then typically it's going to take the residual, the difference between the predicted and observed values, square it and add it up, and that's the objective function, particularly for these kinds of transient analysis. So the objective function for this problem is shown right there. It has that funny name, and I'll show you where that comes from in just a second. And then these are the type and the multiple objectives. These are all defaults. We don't need to worry about them now. We do need to worry about, though, control variables and parameters. These are the parameters that will be adjusted to give us an optimal fit. So we're trying to find these parameters. These are N and alpha. These are the parameters that control the shape of the soil moisture retention curve. So we give them initial guesses and a lower and upper bound, and these will then be adjusted by the parameter estimation algorithm, that Nelder-Mead um, um, algorithm. So we have constraints that are also specified in this file, or in this node. I'll show you where to get that in just a second. And then I have plots that are generated as this optimization routine is run. I selected this one, predicted and observed water content. That's this plot over here, and the dots are the predicted values and the line is the calculated value, and this is going to be shown during each iteration. So we can kind of keep track and see how the optimization routine is doing as it runs. And then also, this is important here, the objective values and the constraints. These are the results of the analysis. The objective table, this is where, let me see, I can show you that. This is here. Okay, it looks like I haven't run this one yet, so I don't have the objective table 10. But this is where the results of N and alpha will be once the analysis is completed. Alrighty, so that's the setup for the optimization node. Now before we run this, we have to set up the objective function, and that's done using this physics node here. It's called optimization, and it's added by right-clicking on component and adding physics. If you then go to mathematics, expand that out, you'll see optimization and sensitivity, and you can select the optimization node right there. Now I did that and added in this optimization node, and this allows you to do a variety of things, and for our applications I selected this global least squares objective. This is the objective function that we want to use, and so when I selected that, I got this node right here, and I'm going to do two things. I'm going to pick the data that are my observations that I want to fit, and then I'm going to pick the variable from within the analysis that has the calculated values that I'm going to compare with the observed values to create the objective function. Alright, so right here I browse for the file, and these are CSV files, comma, separated values, and I pick the one that I want to use. And in this case, the file has two columns. The left column is time, and the next one is the value of water content at that particular time at a particular location that is at x equals 0.5 meters. Okay, so that's the data in this file. Then after I've done that, I go and select time, and I get a node that looks like that, and that will make the first column in the file that gets read in. That's the time column, and then I added, and you don't really have to do anything other than just add that node in there. And then if I right click and specify value, select that, then this one shows up, and that corresponds to the next column in that CSV file that we read in. So that's going to be read in and used as a value that we will compare to a calculated value. Okay, so because it appears second, it uses the second column, and we have to then also give it an expression shown right here that is used within the simulation to calculate the value that we will compare to the value in the data set. Okay, so this expression is comp1.wc_calc. So this is going to be WC is water content calculated. So that's a variable name that I made up, and I determined it so that it would be the water content at x equals 0.5 meters um, in the calculation. And so the way to do it is to go up here to definitions and go down here to domain point probe. What I did, if I select definitions and right click, I go to component couplings. No, that's not it. Probes, sorry, right there. Domain point probe. So I added that, and then I added this thing right here. So when I first added it, then I can select where the probe is located. So I put 0.5 meters because that's the location where my data were measured. And then I add this point probe, and I give it a name here, a label. This is just so that I can remember what's going on with this point probe. And then this is the important one, WC calc. That's the variable name that will be determined at this particular location that I've defined. And that variable name will be determined as equal to this variable, dl theta. So this is a built-in variable, and you can check out other built-in variables here. There's dl theta, it's the liquid volume fraction, the volumetric water content. And the value of dl theta, the water content, is assigned to WC calc, and that creates a data, basically an array of data that's going to be compared to the data that I read in with the file. Okay, so let's go back to the value column. There's that WC calc that's defined by the point probe. The comp1, that's part of the name, and that comp1 comes from the component, which is right there. So all of this analysis here that we've been looking at is a component, and that comp1 right there is right there. So if this is changed, comp1, then that would be changed. All right, so this is the setup of the objective function. I'm reading in a data file and then defining these columns, and for the time columns I don't do anything, but for the value column I have to also specify a variable name that I compare to the data. This is a variable that's calculated. Okay, so that's the setup, and then if I come back here to optimization and go to the objective function, I'm going to just erase the setup that I had. And so if I go to the objective function and go here to optimization, there's the name of the objective function, and I select that, and that a name appears there. And so that's the objective function that I want to use. And I want to also make sure that I've selected this redistribution of water. This is the this third study. I'm sorry, this is the step right here. So actually, that's a good point. Let's go back here to value. This is where we have the setup of the objective function, and I'm giving it this name. If I go to equation, then yeah, this is an important step that I glossed over. So I talked about selecting that variable name. Well, this analysis is a little complicated, right? Because we've got these three different steps. So we want to make sure that we use the value of this variable at calculated during this third step. So to do that, we have to go down here to equation view, and it's show the equation assuming this one, study for combined analysis. There's a variety of studies that we can pick, and so this one is going to be study 4, step, doesn't say step 3, but it's study 4, redistribution of water. Study 4, redistribution of water. Okay, so that's going to be necessary. And then when we come down here to the optimization, we see that it's got the redistribution of water from step 3 done right there. Okay, so that's going to be necessary to get things set up. And then we could have various different optimization or various different objective functions. We can make some of them active and some of them inactive here. We only have one in this case, but this is where we would activate them or inactivate them. And then we'll also have the constraints here. And I think, yeah. So this is basically just going to be the same. For this problem, we just selected the same file right there. All right, so that's the setup for this study. I've got it set up so that I'm including this graphics. When I run it, I will show you what happens. So it gets going. Each analysis runs fairly quickly. Well, I don't really have great display. I'm going to stop this, and I'm going to change it so that I can see this a little bit better. Well, seems to be having some peculiar things with the graphics. There's this gray line here that really shouldn't be there. So all right, that looks a little bit better. Now I'm going to go and run this, and we'll take a look at what this looks like as it runs. So the analysis is going to go through each one of these 3 steps, and that'll calculate the results, and it'll then plot. And you can see there's the results for step 1, and it'll display the values of the parameters that it's using for each step. There, right there, n equals 2 and alpha 2.5, and so it's going to go through the different parameters and adjust them using the optimization algorithm and try different values and try to minimize the residuals between the predicted blue value and the observed dots.